For billions of years, the night sky has been a canvas of sparkling light, a tapestry woven from the fires of countless stars. Each glitter represents a sun, many with planets and perhaps life. But all fires burn out. Even the brightest blaze eventually fades to embers, then to darkness. Tonight, we live in an illuminated era. Our sun still shines, our Milky Way still teems with star clusters, and the universe continues its brilliant glow. Yet over unimaginable timescales, even this vast brightness will extinguish. Every star will die. Every galaxy will grow dim. The cosmos will become a silent, dark void. This is not science fiction. It is the destiny written into the fabric of space-time. In this episode of Skyward Space Quest, we will journey across cosmic history, from the first sparks of starlight to the universe's final lonely epoch. We will witness stellar births and deaths, the slow cooling of white dwarfs, the possible decay of matter itself, and ultimately the heat death of all things. Welcome to the last star, how the universe goes dark. Every star begins life in a nebula, a sprawling cloud of hydrogen, helium, and traces of heavier elements. Gravity pulls these atoms inward, causing the cloud to contract and heat up at its core. When the central temperature and pressure become high enough, hydrogen nuclei begin to fuse into helium, igniting a new star. This transition from cold cloud to blazing prototype marks the start of the main sequence phase, during which a star shines by converting hydrogen to helium in its core. Main sequence lifetimes vary dramatically. High-mass stars, those with at least 8 times the mass of our Sun, burn through their nuclear fuel in mere millions of years. Their cores fuse heavier and heavier elements until iron forms, triggering a catastrophic supernova explosion that leaves behind a neutron star or black hole. Stars like our own Sun, with about 1 solar mass, enjoy roughly 10 billion years of stable fusion. Once hydrogen runs low, they swell into red giants, fuse helium to carbon and oxygen, and eventually expel their outer layers as planetary nebulae, revealing their hot cores as white dwarfs. The universe's most common stars, low-mass red dwarfs with less than half a solar mass, burn so efficiently that their main sequence lifetimes may reach trillions of years, orders of magnitude beyond the current cosmic age. These stars never become red giants, but slowly fade into white dwarfs, only after exhausting their hydrogen. The fate of each star depends largely on its initial mass. Yet, regardless of mass, the end comes when nuclear fusion can no longer support the star's core against gravity. Massive stars end with supernovae, forging heavy elements that seed future star formation. Intermediate mass stars peel away layers to expose white dwarfs. The lowest mass stars fade directly into white dwarfs. Throughout the universe, this cycle of birth, fusion and death plays out billions of times per second, but it will not continue indefinitely. As galaxies exhaust their gas supply and stellar nurseries empty, fewer new stars will form. Eventually, the cosmos will see only the dying embers of long-dead stars. When a sun-like star sheds its outer layers, it leaves behind a white dwarf, a dense sphere roughly the size of Earth, packing half a solar mass into a volume millions of times smaller than the original star. Initially, white dwarfs glow at temperatures exceeding 100,000 Kelvin, radiating their stored thermal energy, but lacking internal fusion, they gradually cool. Astrophysicists project that in about 100 trillion to 1 quadrillion years, a white dwarf's surface temperature will drop below 5,000 Kelvin, the point at which it no longer emits significant visible light. Beyond this, it continues cooling, eventually approaching the cosmic microwave background temperature. The final stage, a black dwarf, is a white dwarf so cold it emits no detectable radiation in any waveband. However, the universe's current age, 13.8 billion years, is too young for any black dwarfs to exist. We are still firmly within the stellar era, witnessing the last bright flames before darkness. Once the last red dwarfs fade into white dwarfs, which may take 10 trillion to 100 trillion years, no new stellar light sources will remain. The universe will be populated by dim, cooling embers, sliding into oblivion. Beyond the stellar graveyard lies a subtler decay, the potential instability of matter itself. Many grand unified theories, or GUTs, predict that protons, the building blocks of atomic nuclei, may not last forever. Instead, they could slowly decay into lighter particles, such as positrons and neutral mesons. This process, called proton decay, is hypothesized to have a half-life around 10 to the 34th to 10 to the 36th years. If confirmed, it means that even the stable nuclei of white dwarfs will eventually disintegrate. Over 10 to the 35th years, half of all protons will have decayed. Over 10 to the 36th, 3/4 will be gone. As protons vanish, atoms crumble, releasing energetic particles into the cold void. Hydrogen, the simplest atom, is prone to decay first. Helium and heavier elements are also unstable, though some isotopes may survive longer. In a universe where proton decay occurs, all baryonic matter, stars, planets, gas and dust, will eventually disappear. Long after black dwarfs have faded, the cosmos will contain only a dilute sea of electrons, neutrinos, photons, and whatever dark matter endures. Observations of distant supernovae and, well, the cosmic microwave background reveal an accelerating expansion of the universe driven by dark energy. As galaxies rush away, they cross each other's cosmic horizon, becoming, forever unreachable. In thermodynamic terms, the universe is moving toward maximum entropy, a state of heat death. This term describes a cosmos so thoroughly dispersed that no energy gradients remain to perform work. Key phases toward heat death include, first, the degenerate era. After star formation ceases, roughly after 100 trillion years, white dwarfs, neutron stars and black holes dominate. Next comes the black hole era. Between 10 duodecillion and 1 googol years, black holes slowly evaporate via Hawking radiation, releasing their mass energy back as photons and particles. And finally, the dark era. Beyond 1 googol years, all black holes have vanished, protons have decayed, and only a few stray particles remain. During the degenerate era, occasional collisions between stellar remnants may produce brief flashes of radiation. Similarly, quantum tunneling could form microscopic black holes or particles, but these are, rare anomalies in an otherwise featureless cosmos. As usable energy vanishes, no engines, biological or mechanical, can extract work. Structures disintegrate, even atoms themselves may break apart if proton decay holds true. In the latter half of cosmic history, black holes, birthed from the gravitational collapse of massive stars or formed at galactic centers, become the longest-lived structures. Stephen Hawking's groundbreaking insight revealed that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes them to lose mass over time. Now stellar mass black holes, with masses around 10 times that of our Sun, evaporate over roughly 10 to the 67th years. Supermassive black holes weighing in at 100 million to 10 billion solar masses last far longer, on the order of 10 to the 95th to 10 to the 104th years. As a black hole shrinks, its temperature rises, accelerating the final phase of evaporation into a burst of high-energy gamma rays. This might be the last bright event in an otherwise dark universe, a fleeting flash, then nothing. Once all black holes have vanished, the universe enters its darkest age. Only a cold, diffuse plasma of elementary particles remains, spread across an ever-expanding void. Beyond even black hole evaporation lies the realm of quantum fluctuations and vacuum metastability. Some theories propose our universe exists in a false vacuum, a local energy minimum that could, via quantum tunneling, decay to a lower energy state. Such a vacuum bubble would expand at nearly light speed, rewriting the laws of physics within. Any structures it encountered would be obliterated. Alternatively, in an almost perfect vacuum, quantum fluctuations might sporadically produce particle-antiparticle pairs or even miniature black holes. But these events would be isolated and ephemeral, leaving the cosmic backdrop largely empty. Over 10 to the 1000th years or more, space-time itself may approach inherent instability. Yet for all practical purposes, the universe will remain a quiet, inert expanse devoid of stars, galaxies, or any structure. Our existence, a mere 13.8 billion years after the Big Bang, is a fleeting spark in the grand tapestry of cosmic time. We witness the universe at its zenith of brightness, but the candle will not burn forever. Life, consciousness, and civilization are temporary phenomena. We emerged in a universe still rich in energy and structure, capable of sustaining complex chemistry and biology. In the cosmic future, none of that remains. Yet in this brief window, we have gazed at the stars, probed the heavens, and asked fundamental questions. Where did we come from? What is our fate? Are we alone? The approach of cosmic darkness reminds us of life's value and fragility. It underscores our responsibility to preserve knowledge and wonder, to carry forward the flame of curiosity even as the universe dims. From the first glimmers of starlight to the slow fade of white dwarfs, from proton decay to the final evaporation of black holes, the universe's story is one of brilliant beginnings and inexorable endings. We live in the brief interval between cosmic dawn and perpetual night. It is our privilege and responsibility to explore, learn, and share this grand narrative. If this voyage through time and space moved you, please like, subscribe, and tap the bell on Skyward Space Quest. Join us each week as we unravel the mysteries of our cosmic home, from the smallest particles to the farthest galaxies, from the first stars to the last. Until next time, keep looking up.